there's one more piece of chapter 1 that we're going to need to cover, and that's to introduce vector math, the algebra that goes with vector quantities, and we'll talk about that in a minute. Because we won't need that content until Wednesday, and because I don't want to overload you with lectures to watch over the weekend, because that's crappy. I'm going to skip ahead to chapter 2, and I'll lecture a bit about chapter 2, and then later on this weekend, or maybe on Monday, I'll post the rest of the videos for the rest of our first week, so that you can watch them in preparation for Wednesday and Thursday. Okay, so chapter 2. Chapter 2 introduces the equipment that we'll use to talk about motion. For now, let's restrict ourselves to motion along one direction, so that we can get a handle on how this equipment works and the ways in which we can math with it. Let's stay single direction, motion along one direction only, whatever direction that is. Doesn't have to be in any particular direction. It could be that way, whatever. But so that if we were going to draw a coordinate system to, attach to that motion, the motion would be entirely along an axis that we could define. For simplicity, let's call it the x-axis for now. But it could be the y, it could be the z, it could be the q, like whatever axis you want to talk about, we'll talk about that. But just so that we're on the same page, let's talk about the x-axis. So on a normal Cartesian system, we would draw the y-axis up and down the page and the x-axis across the page, positive to the right. Let's use that convention here, and let's talk about motion to the right. In order to talk about motion, we need to talk about place. Something is here, and then later it is there. Where is here? Never mind there. Where am I right now? I could tell you I'm in my office, but that doesn't do anything for you. You don't know where that is. I could tell you that I am 1.3 meters away from the door to my office, but again, that doesn't do anything for you. You don't know where that is. For all you know, it's on the moon. I could say that that I'm in Temple Hills, Maryland, and that would at least put me on the Earth somewhere in Maryland. And we'd have to go look up where Temple Hills is in Maryland, but that's a pretty big area. The point is, we need, I could, wander around Temple Hills for a while, specifying landmarks and trying to figure out a way to specify exactly where I am relative to somewhere. But the point is, relative to somewhere. That's really what I'm aiming for. We need an origin, and we actually already drew one. We just tend not to think about it. In order to talk about place, we need to agree from where we are measuring the location of that place. We need an origin. Then, if we are here, we need a way to talk about where that is. And since we're on the x-axis, the easiest way to talk about it is to specify it with some coordinate x1 and some coordinate here as x2. We need a coordinate to express for us the distance. It's just a length. The distance of our position from the origin. Relative to the origin, we are at x equals x1. If we were to the left of the origin, somewhere over here, then our x coordinate would be negative, and that's how we would indicate that it's along the x-axis to the left as opposed to the right. So these coordinates could be signed, or one could be positive, one could be negative. That's totally fine. Their magnitude, the size of them, the absolute value, tells us how far away we are from the origin. The sign tells us which direction, left or right. Okay, cool. We're going to talk about motion. So that means our position has changed. We started at x1, now we are at x2. Let's give these values just for the sake of argument. Let's say x1 was 2 meters and x2 was 5 meters. So by how much has our position changed? And you immediately answer 3 meters, and it's because you already know how to do this. When we want to talk about change in position, we always mean position final, where we ended up. Position final, use an F, minus position initial. I'll use an I, F and I for final and initial. I don't want to write this in words every time. Position X. That's the variable that we're using to track where we are along this axis relative to the origin. Equal position F, that's X2. We could say X final for now, just for this, to be really careful. X initial. We know that that's, in this case, X2 minus X1. If we had started at X2 and gone back to X1, then this subtraction would be reversed. This one would stay as is. It's always where we end minus where we started, wherever those are. Change in X. Change in is an idea, a concept, a word, phrase that we're going to use over and over and over again. I'd like to have a symbol for that as well. Triangle. It's a capital Greek letter delta, and that's going to be our symbol for change in. Anytime we see delta, it means change in whatever symbol comes after it. So sometime later, I write this. I don't know what smiley face is, but this is the change in smiley face. Whatever variable smiley face represents, apparently its value has changed. We're talking about that. Delta. Okay. Change in position is 5 syllables. Again, I'm lazy, fundamentally. I don't want to say that many syllables. I'd like to give that a name, and ideally, reduce the number of syllables. Origin, position, displacement. If we're going to talk about the change in position, we are talking about displacement. Displacement is other than distance traveled. Let me explain what I mean. If we start at x1, go to x2, and then come back, displacement is the change in our position. We ended at x1, we started at x1, so our displacement is 0. It's sort of like you saw me at x1, you looked away, and then you looked again, and I was at x1. So you say, well, your position hasn't changed. What you don't know is that I walked to x2 and came back, but we didn't see that. From beginning to end, there was no change in position. The displacement is 0. If we want to talk about distance traveled, we're going to have to go calculate that kind of manually. divide the motion into pieces, never mind, and kind of unsign the motion to the left. We walked 3 meters this way, and then we turned around and walked another 3 meters, but we covered a distance of 6 meters. Our displacement was 0. All right, so we've talked about, so far, 4 definitions: origin, position, displacement, distance, and then the 5th, the delta construction, change in whatever. So far, so good? Cool. I'm going to switch to a more two-dimensional axis system. But this is not X and Y. This is not 2 spatial dimensions. This is the dimension of space that we're tracking here and time running horizontally. So as time increases, we're asking, what is our position? Suppose we're talking about 2 different motions. 2 different motions between x1 and x2. Let's say that at time 0, one object starts at x1. You know what? Let's not make it 0. Let's say that at some time t1, one object, I'll use the black marker for that, starts at x1. At some time t2, that object is at x2. So it took an interval of time delta t is always final minus initial because delta. So that's t2 minus t1. An interval of time this big for us to change our position by delta x. We could talk about, we could define a rate at which we changed our position. And we could, we might be interested in doing that. Suppose there was another object that also started at x1 at t1, but then didn't get to x2 until some other time t3. The object in the blue ink didn't cover the same displacement in as much time as the black ink. It took more time to achieve the same displacement. So it didn't occur as quickly. It occurred at a different rate on average. So let's define the average rate at which position changes. So average rate of displacement. We're going to define that as displacement per elapsed time. 3-line equals is defined to be. It is not equal for any other reason than because we're saying so. And we want to give this a name. Let's call it velocity. Okay, cool. On average, it took this object so and so much time to go so and so much distance. And actually, this is on this coordinate system, it's the vertical change divided by the horizontal change. We just calculated the average slope between these 2 points. When we say velocity, apparently, what we mean is the slope of a graph of position versus time. See, but we didn't actually have a graph of position versus time. We just had 2 points. We found the average slope between them, but that might not actually be the whole story. I mean, just to finish this story, the average rate of displacement for the other object, just trying to conserve my blue ink here, it took more time to travel the same displacement, so it isn't going as fast. And we can see that expressed, this slope is not as steep. It's not as steep a slope. The velocity is less. And that's the way that we'll keep track of the fact that it's moving slower. It's not changing its location as quickly as the other object, on average. And that's the piece I want to unpack right now. Okay. Let's talk about a third kind of, just to kind of get an idea for what's going on here. Suppose there were a third position, x3. Note that they don't have to be, in any particular order. I'm just giving them names. It's like calling them, Larry, Curly, and Moe. We could call them something else. It doesn't matter. X3 is between x1 and x2. Oh well. It's okay. The labels and the names, they're for us. So it's just a matter of keeping track. This is the third position that I've labeled. I'm going to call it x3. Suppose we first go from x1 to x3, and then from x3 to x2 in time t3. If we talk about the time interval between t1 and t2, on average, we're going to get from x1 to x3 in that much time. And then if we talk about the interval from t2 to t3, we're going to get from x3 to x2 in that much time. And the thing is, these slopes are different. If we keep this line going, that slope is different from this slope. So depending which interval we're talking about, we're going to get a different answer for how fast this object was moving. And then there's a third, like if we ask about overall for this entire motion, there's a third answer we're going to get. And it's the slope just between those 2 points, which is different, presumably, from either slope in either interval. So there's kind of a problem with our definition, is that our definition for velocity is only right now permitting us to talk about average velocities. And if we talked about the average velocity during the entire interval t1 and t3, the answer we get would not be the actual velocity with which our position was changing during either interval. But what if we want to know how fast we were going at t2 or at this time, whatever time between t2 and t3? Okay. Suppose our position versus time graph looked like this. For a while, the slope is very small, almost zero, and then later it becomes steeper. What we'd like to talk about is how steep is the slope at any given time. If we calculate the average velocity between these 2 points, we've got the the line segment between them, delta x over delta t, average velocity. But there are many points along this curve where the slope is less than that, and many points along where it's greater than that. And we can see that because there's a pretty big gap between the average velocity and the actual curve that describes the motion. What if we consider a smaller interval? What if instead of this one, what if we talk about this interval? Just from T2 to T3. The average velocity calculation for that interval would only be that, and is less different from the actual curve than the blue curve is different from the actual curve for the larger interval. Which makes me think that, all right, what if we considered an even smaller interval? And the average velocity calculation for that interval is almost the same as the curve itself. Well, how almost the same? How almost is almost? All right. Well, what if we want infinite, well, arbitrary precision? So let almost be as small as you could ever want. Let's talk about an average velocity calculation. Between 2 points, between 2 times, let's say. So it's the position at some time 3 minus the position at some time T2. And we just keep moving T2 around. I don't know. Suppose we let T2 be as close as you want to T3 without actually being T3. You know, if T3 is 3 seconds, let T2 be 2.9999999999999, as close as you want, just not actually mathematically equal to 3. What we're doing is taking the limit. We're asking for the limit of this as T2 approaches T3. And that's going to get us the best possible agreement between the average velocity calculation and the curve itself, because they're basically the same point. We're basically talking about 2 points right here, and we're talking about the slope between them, which turns out to be the slope of the line tangent to our function. We've got a derivative. The actual velocity as a function of time. This is not multiplication. This is velocity as evaluated at time t. Is the time rate of change of the position as a function of time. And this, again, it's a 3-line equals because it just, it's derived from our original definition of average velocity as the slope of the it's called the secant line, is these 2 points. The actual velocity at any given time is the time derivative of the position. When we first defined derivatives as functions, we said that's what we wanted. We wanted a function that would, at all points, tell us its value is the value of the slope of the function we're interested in. That's what we want from velocity. Velocity every time is calculated as rise over run. So that's slope. What is the slope here? It's the slope of the tangent line, and derivatives are the mathematical equipment that we're going to use to keep track of that. I mean, that's how we got to them in the first place. Okay, cool. In the interest of time, I'm going to move very quickly through the next piece, and that is to say that what if our velocity changes? Okay, well, we could use exactly the same equipment to talk about the fact that our velocity is changing. We could define an average rate of change in time, and we could call that the rate of velocity change. That's a lot of syllables, so maybe we could call it, I don't know, just off the top of my head. Let's call it the acceleration. So let me make a list over here of some definitions that we've got. We have talked about displacement. Delta x equals x final minus x initial. We've talked about velocity as the displacement divided by the time that went by. We've talked about the instantaneous velocity as the derivative of the position function. And if you'll permit me, I'll just define an average acceleration A as change in velocity divided by elapsed time. Define 3-line equals the time rate of change of velocity, the rate at which our velocity is changing. Let's call that acceleration. And in a very similar way, since this is only an average, we're going to need calculus to talk about the instantaneous value. Velocity, the velocity function is itself the derivative of the position. So what we have said is that this is the time derivative of the time derivative of position, or that's equal to the second time derivative of the position function. Okay. Suppose I told you the acceleration function, excuse me. Suppose I told you that the acceleration is some function of time. How could we talk about the velocity? Well, all right, if they are related by derivatives, then if we integrate, we can talk about the reverse relationship. If we d by dt, if we treat this just really quickly like a small differential equation and integrate both sides. The integral of dx is x, the integral of dy is y, the integral of dt is t, the integral of dv is v. And we're taking the integral with respect to time of the acceleration. There's going to be an integration constant associated with this indefinite integral, and that's related to the initial value of the velocity that we need to know. We have the velocity at time t. What was it at the beginning of the interval? At time t after the interval. So we can talk about the change in the velocity. We also need to be given an initial value. It's an example of an initial value problem. So on Tuesday, we'll practice analysis like this. That's as much as I want to say about it for now. We'll dig into it more on Tuesday. Just wanted to point out that we can do it. There's a family of kinds of motion that we like to talk about, and that's a motion for which the acceleration is constant. Not necessarily zero, just constant. If the acceleration as a function of time is just some constant a0, it's that value all the time, it never changes. The rate of change of our velocity is constant. Then when we integrate, when we say that velocity as a function of time is the integral of the acceleration as a function of time dt, what we're integrating is the integral a0 dt, which is just the a0 is constant. We can pull it outside the integral. A0 integral dt. Integral dt is just t plus an integration constant. The integration constant here is the value of the right-hand side if t were 0. The velocity when t is equal to 0 is capital C. That's our integration constant. So I'm actually going to give it a name. I'm going to call it initial velocity. Cool. If we wanted to integrate again, we know that the position is really related to the velocity by integration, or by calculus. So we could ask for the position function by integrating the velocity function. But we just found the velocity function. A0t plus v0 dt. So we can integrate, okay, integral t dt gets us t squared over 2 times the coefficient a0. v0 is constant. Integral dt is just t plus the constant of integration. If t is 0, then we're talking about x at time 0, which is 0, 0, just capital C. So here again, we're talking about the initial value, x of 0. Okay. So we have one equation that is true for constant acceleration. We have another equation that is true for constant acceleration. There are 2 more that I'd like to have in that drawer of our toolbox for constant acceleration problems. To prove them, I've got to erase the board. So I'm just pausing for a second to make sure that you've got everything that you want. and down. Not that you can't pause it and come back to it, just stalling for a second. I'm sorry that this video is kind of long, but it doesn't really make a lot of sense to put it into chunks. I guess, well, maybe I'll still, if the acceleration is constant, that's what we're talking about here now. Acceleration equals 0. Think back to your calculus and recall that there is an average value formula for integration. And if memory serves, the average value of a function f on an interval from a to b, and I'm using this weird triangular notation, it doesn't matter. The average value of a function f on an interval from a to b is the integral of the derivative of f along the interval from a to b. So in other words, what is the total change in f from a to b, and then over what interval does that occur? I think that's right. But just for the sake of argument, let me look that up. See, nope, I got that wrong. that's yep. Having good notes is really important. It's not the derivative, it's just the function. Does this formula make sense? Here's some function. Here's an a, here's one b. The integral of the function from a to b is going to get us to this area. If we then divide by b minus a, the width of that area. So this is an area. We're dividing by the width. That's going to get us the length, or the height, I guess, of the average rectangle that represents this rectangle. Or this isn't a rectangle. The average rectangle that represents this area. What rectangle could we draw such that the area underneath that function is the same as the actual area underneath the function itself? Because we could represent, on average, it looks like the function has this value, because the integral of a function whose value is that constant is the same as the integral of our actual function. So we could represent our actual function with this value on average during the interval. Cool. Average value formula. Okay. Suppose I were interested in the average value of the velocity. Velocity average from A to B. Velocity average from A to B. Let's do it that way. We're tracking times. t1 to t2 on some interval, the average velocity, would be the difference. We're going to divide by the width of that interval and then integrate from t1 to t2 the function itself. That's an application of the average value formula, the mean value theorem for intervals. Okay. In the case of constant acceleration, we know what this velocity formula looks like. It's the initial plus the constant acceleration times the time, dt. Okay, well, let's see what we get. T2 minus T1. The integral here gets us V0t plus 1/2 A0t squared, evaluated from T1 to T2. Okay, so that's equal to, or T2 minus T1. We've got to plug in T2. V0 T2 plus 1/2 A0 T2 squared minus what we get when we plug in T1. V0 T1 plus 1/2 A0 T1 squared. With me so far? So again, we went from here to here. Okay, let's distribute the minus sign so we don't need that parentheses anymore. Okay. Inside this expression, let's group terms according to, we got V0 T2 minus T1 and 1/2 A0 T2 minus T1 squared. T2 squared minus T1 squared is the difference of squares, so we can factor that. V0 T2 minus T1 plus 1/2 A0 T2 minus T2 plus, and we're going to divide the whole thing by T2 minus T1, which we have in each term. So we've got a new expression, V0 plus 1/2 A0 T2 plus T1. That is a very strange expression. That would be the average value of the velocity on some interval. Very strange. It's a very strange expression, and it's not what I expected it to look like. And the reason it doesn't look like what I expected it to look like, and I'll show you what it's supposed to look like in a second. The reason it doesn't look like I expected it to look is because I've done this wrong. When I plugged in v0 plus at as the velocity function, that was, that was here. V average from a to b is equal to the integral of v0 plus at dt from t1 to t2. This expression we arrived because we integrated a dt from t1 to t2, I guess, or from 0 to some other time, from 0 to t. So we ended up getting at plus the velocity that we have at time 0. Or if we go from t1 to t2, we've got a times t2 minus t1 plus the velocity that we have at time 1. Or at t1, excuse me. That's really what I should have put into the integral for the velocity function if we're going to go from t1 to t2. Because that velocity function goes from t1 to t2. That's how we arrived at it. So for the sake of argument, I think we should go back and fix it. The punchline, I'm going to fix it. The punchline is that what we've essentially said by writing v0 is that t1 is 0. This is the velocity that we talked about at the beginning of the interval, v sub 0, when time is equal to 0. So this t1 that we're talking about here, that's actually 0. And that means we can write this 2v0 plus a0 t2 all divided by 2. Find a common denominator for the half and then add. And we can separate the two v0s. Let's write it as v0 plus v0 plus a0 t2 all divided by 2. Now v0 is the initial velocity, and v0 plus at is the actual velocity later. It's the initial velocity plus the final velocity divided by 2. It is literally just the average of the initial and the final velocities. And that trick works because the acceleration is constant. Just really quick, if we graph the velocity versus time, a constant acceleration means that graph is linear, and the area underneath that looks like this. if we represent that with a rectangle squared off halfway between the two velocities in question, then we've satisfied the average value theorem, and it's just a rectangle as tall as the average between the top and the bottom, because it's linear, because we need these two triangles to be congruent. Okay. I'll tell you what, I'm going to keep going from here with the result that I've derived, or not really derived, but claimed that I could derive if I did it right. I'm going to keep going from here, finish our material, and then in another segment, fix the derivation so that you can check through it and make sure that I'm not crazy. Okay, so for now, let's keep this. I'll put that result here, that the average velocity is the initial plus the final for an interval divided by 2. And instead of final, I'm just going to leave it. This one's the initial, and this one's the velocity at the end of the interval. Just so that way there's less, fewer subscripts in our algebra. The average velocity we know is the displacement divided by the time. And we also said that the final velocity should be the initial velocity plus the acceleration times the time, if the acceleration is constant. And so this is true if the acceleration is constant. This is true if the acceleration is constant. This is true all the time, by definition. Okay. So if we solve this for time, v minus v0 over the acceleration, that's how much time has gone by to get us from this initial velocity to this final velocity. So when we cross multiply here, equals delta t v average. Delta t we could express this way, if the acceleration is constant. And v average we could express this way, if the acceleration is constant. That looks like the difference of squares the other way. So this looks like v squared minus v0 squared over 2 times the acceleration. And that's the last formula that I want to have in our toolbox for constant acceleration. Usually we write it this way, that v squared is equal to v0 squared plus 2 the acceleration times delta x. Okay. Those equations are going to be useful for us in Monday's work. And then we'll practice more with them on Tuesday. And that's as much as I need to present in order to get us ready for Monday and Tuesday. So I'll stop there. One more segment after this to fix the derivation that I screwed up a second ago. And more videos to come on Monday to prepare us for the rest of the week. Thanks, everybody.